So in this case, if we look into the convex problem classes, there are different problems classes. So convex problems can also be subtypes, and some subtypes are easier to solve than the other ones. For instance, one example is linear programming. In linear programming, all convex constraints, objective function, as well as the inequality constraints are linear. So as you see here, in this case, this was f0x. If you remember, for general convex problem, this was convex f0x function. And in this case, in linear programming, that becomes a linear function. So in this case, that becomes C transpose X plus D. And inequality constraints, if you remember, which was Fix, again, this is a convex function, which is inequality constraint. So in this case, G times X should be smaller than H. And again, we have the linear constraints, linear equality constraints, AX equals B as the equality constraints. And in convex problem, we have an affine objective. So if you noticed, this is an affine function of X, and constraints are also affine function of X. And in this case, the feasible set is guaranteed to be a polyhedron. As we have discussed in the convex set, when we have these half spaces and hyperspaces, and defined by basically the inequality constraints, then the polyhedron becomes their intersection. And in this case, that's why we have this polyhedron as the feasible set. And linear programming is a programming that we'll use a lot in this course, and that's quite useful in practice. And again, there are subtype of linear problems. So for instance, in this case, we have L1 norm minimization as well as L infinity norm minimization. So both of these problems are basically linear program. And again, in the slides, you can see that how we can transform the infinity norm, which is basically minimizing the maximum entry in the X vector into a different LP form as you see here. And again, for L1 norm is basically the absolute value, summation of absolute value of all vectors. So L1 norm, just a sec, L1 norm is basically for summation of entries, I is 1 to n, for all entries in the vector. Absolute value summation of all entries in the vector. So this is an L1 norm. And again, this can be turned into an LP problem, where basically each entry in the X is bounded by T vectors, and T's are the ones that we try to minimize. So we are taking basically the summation among these Ti's, where Ti's are absolute value of Xi. And in this case, the absolute value is represented like this. So for each I, we have minus Ti is smaller or equal than Xi, where Xi is smaller or equal than Ti, which will be a linear constraint. And again, linear fractional programming is another programming problem where we have, it's similar to the linear programming problem, but we have division of two linear or two affine function. And in this case, for instance, in this case, the objective function is different. It's C transpose times X plus D divided by E transpose X plus F. And similarly, inequality and equality constraints. And in this case, basically, this is a quasi-convex optimization problem. And we do not know to know the details, but there are certain methods that transforms this problem into a LP problem. So that's what you should know. So when needed, we have certain methods that transform the linear fractional problem to linear problem. And another problem is quadratic programming problem. So quadratic problem, again, the constraints are linear. So we have the linear equality and linear inequality constraints. But the objective function is not linear. The objective function is quadratic. So in this case, the objective function is 1 divided by 2 x transpose px plus qtx plus r. So this is the quadratic function that we have seen before. And this is, as we have seen, this is convex when its Hessian matrix is greater than 0, and its Hessian matrix, which is from the second derivative, basically second order condition, should be basically greater or equal than 0. So matrix greater or equal than 0 means that it's basically a positive semi-definite matrix. An objective function is convex, but the constraints are affine constraints and linear constraints. And again, minimization of such convex function is defined over a polyhedron. So we have the polyhedron made up of the intersections of these functions. And basically by looking at the gradient of the objective function, which is f0, we are basically trying to find the minimum point on the boundary of this polyhedron in which this quadratic programming or this objective function is maximized. Another type of problem is quadratically constrained quadratic problem. So in this case, basically this is similar to quadratic programming case, but the difference here is that the inequality constraint is also an basically second order constraint. So previously it was only qi transpose x plus ri, so it was only linear type, but here we also do have basically second order or quadratic terms. And however, in order this to be a convex problem, so the objective is convex. In order objective to be convex, P0 matrix here should be positive semi-definite. And again, in order this quadratically constrained quadratic problem to be convex, we need to have PIs in the inequality constraints to be positive semi-definite as well. So PI is greater than 0 as well. So this is 0. Maybe let me rewrite. So P0 is greater than 0, and Pi is also greater or equal than 0. Since these are satisfied, this becomes the quadratically constrained quadratic problem. And there are other type of problems as well, but we don't use much in this course, such as second order cone programming and semi-definite programming. So again, second order cone programming is more general than quadratically constrained quadratic problem and linear problem. And it's basically a convex problem. And semi-definite problem is more general than all of them. So it's like the problem class includes all problems or all convex problems like linear programming, linear fractional problem, and quadratically formulated convex programming problems in itself. And there are certain methods to solve these problems as well. And this is it for today. Before finishing, so there are certain libraries for optimization. So there is a CVX library, so CVX opt library. So there are CVX, CVX Python. So CVX Py is a Python version of these libraries, so we'll use in this course. And in this case, you can take a look at these libraries. So they are available in many of these languages. And there are other specialized solvers as well, such as, for instance, STP solve, which is for semi-definite programming. But there are general solvers like CVX as well. Okay, so this is it for today. I think we are up, so it's 11:30. So on next week, we'll start the portfolio optimization. So we'll start with a primer on financial data set. And then we'll see, after the primer on financial data sets, we'll see how we can use the techniques we have seen for portfolio optimization, or optimization of a portfolio among number of asset classes.